So thank you for introduction, Sangil. Thank you for borrowing the equipment and solving all the technical problems at the beginning. I was a little bit scared that I will have to give a Blackboard talk, and I'm quite happy that wouldn't be the case. So today's topic is the removal lemma for systems of linear equation, and this is a joint work with Oriol Serra from Barcelona and his former student Louis Vena, who now moved for his PhD to University of Toronto. So first I would like to recall the statement of the classical graph removal lemma. Then I would like to explain the statement of removal lemma for group equation as it was proven by Ben Green. And I would like to present a short and, I believe, elementary proof of this lemma from the graph removal lemma. And at the end of the talk, I would like to talk about another version of removal lemma, another algebraic version of removal lemma, in particular about the removal lemma for systems of equations, which was conjectured by Green. And if time permits, I will probably say a few words about its proof, but I am not sure that I will be able to give too many details, so maybe I will just sketch some ideas behind it. So maybe I should recall what a graph is, who I believe that in discrete math seminar most of the people will be familiar with. So a graph is a pair, you have vertices, you have edges, and every edge joins two of the vertices. So the graph removal lemma in its simplest form says that if you fix a graph H, which has small h vertices, and you're given a huge graph G. So think of H as something small, maybe a triangle, or a cycle of length 4, or a complete graph of order 4. And think of G as some really huge graph, with million or a billion vertices. And there are two possible outcomes. So either G has lots of copies of the graph H. So by a lot of means, so for instance, if you have a triangle and G has n vertices, so you can find n cubed triangles in your big graph G. Or if the number of copies of H is small, so I'm using this notation little o of n to H, so H the number of vertices of the capital H, then you can find few edges, and few means subquadratic in this sense, such that if you remove this set of edges from your graph, there will be no copy of H left. So maybe let me meditate a little bit over this exponent of this small h and this 2. So if you have a graph H on small h vertices, the maximum number of copies of your graph H that you can hope to have in your big graph G is of order n to h. Because simply, if you're really lucky, on every h tuple of vertices, you will find a copy of your big graph H. So the lemma says, if the number of copies is asymptotically smaller than the maximum number of copies you can hope for, then you can remove few edges, and few is again like the number of edges in your graph is at most n choose 2. So again, it means if you find asymptotically less copies of H, then you can expect that at the best case you can remove few edges, meaning subquadratically few edges, such that there will be no copy of H left. And since this is the first time I am using this little o notation, I want to be a little bit more precise at this point and say exactly what I mean by that. And by that I mean that if you fix H, then for every epsilon there will exist some delta, which depends on the graph, on H, and on epsilon, such that if the number of copies is less than delta times n to H, so this is the delta you look at here, then you can remove few edges, and few means at most epsilon times n squared in such a way that your graph becomes H3. So the smaller epsilon, of course the smaller delta, but the important thing is that for every positive epsilon there exists a positive delta, with this property. So maybe just an illustration. So these are the two possible outcomes if H is a triangle. So you're looking at your big graph, and either you see a triangle almost everywhere, so this is this possible outcome, or the other outcome is you find few edges. In this case, you find two edges, such that if you remove these two edges, there will be no triangle left in your graph. So again, the statement of the lemma. So maybe this might be a good time for questions if there are any. So it doesn't seem to be the case. So one of important applications of the graph removal lemma and its variants is in the property testing, which was introduced by Rabinfeld and Sudan. And the idea behind algorithms in this area is that you have some graph property which is invariant under isomorphism. So for instance, you can think of your graph being triangle free, and you want to decide whether an input graph has this property. But your input graph is really huge, so you don't have a time to go through the whole graph, and you only want to scan a small part of your input graph. Of course, such an algorithm cannot always answer correctly, because if you don't search the whole graph, you cannot be sure there is no triangle in your graph. But you will be happy if the algorithm doesn't make an error if the graph is full of triangles. So what we want the algorithm to do, so if the graph has the property P, so if it's triangle free, it should always accept. And if it doesn't have this property, and doesn't have it in a strong sense, but it's something which is called epsilon far, meaning that in order to if you want to change graph G to have the property P, you have to change either to include or to remove more than epsilon times n squared edges. So you have to change a big part of the graph. So if you have to change a big part of your graph, then the graph is said to be epsilon far, and if your graph is epsilon far from having the property P you're interested in, then you should reject. You should reject with probability, and this should be at least 1 minus epsilon. So the removal lemma provides us a tool for designing such algorithms, which can tell you some properties about a big input graph by testing only a small part of it, and with high probability telling you the properties about the whole graph. So during this talk, I will not be that much interested in the graph removal lemma, rather algebraic. I'll have some algebraic versions of removal lemma, but I will be using the graph removal lemma in the proofs. So the central question of the talk will be whether we can say something similar to the removal lemma about some other objects, in particular objects coming from algebra. So now I am coming to the second part of my talk, where I will spend probably most of my time, and this is the formulation, and I will try to give also the whole proof of the removal lemma for group equations. So this is the statement of the lemma. It's quite a recent theorem of Green. He derived actually a regularity lemma for groups, for abelian groups, and from his regularity lemma as a corollary, he derived this removal lemma for groups. So what does the statement say? So you fix M. M will be the number of variables that appear in some equation over an abelian group G. And when the lemma says that for every abelian group G, which has some order capital N, so this capital N will appear like a parameter, like before we had a graph G of order small n with small n vertices. Now we will have an abelian group G which contains capital N elements, and we will be interested in solutions of these equations, x1 times x2 times xm equal to G, and the restriction will be that the ith variable should have a value from the ith set. So we also given sets A1 to AM, and the only solutions we're interested in are such that x1 is chosen from A1, x2 is chosen from A2, x3 is chosen from A3, and so on. And when there are two possible outcomes, so either you have you have lots of solutions, and what does lots of solution means in this case? So lots of solution means the number of solution is of order n to m minus 1. And the maximum number of solutions you can hope for is n to m minus 1, because when you fix the first m minus 1 variables, there is always a choice for the last one, assuming that all the sets would be equal to all the elements of the group. So the maximum number of solutions, or the number of solutions, if unrestricted, of this equation is n to m minus 1, because once you fix m minus 1 of the variables arbitrary, there is a unique choice for the last one. And if the number of solutions is asymptotically smaller, when there exist subsets of the original sets that were restricting the values of the variables, these subsets are not too small, are only sublinearly smaller. So these sets are subsets of the group elements. So where maximum size is linear in the order of the group. And what I am saying here, you can remove sublinear number of elements. So this I prime, the new set, is only a little bit smaller. And there will be no solution such that xi, that all xi's would be from ai primes. So before, if you recall the statement for graphs, in graphs, the removal lemma was saying, if you have few triangles, you can remove few edges and there will be no triangle left. The removal lemma for group says, if you have few solutions of your equation, you can remove few elements from each of the sets that restricts the variables. So this means few, and there will be no solution left. So it's the same kind of phenomena that if you see few objects of a certain kind, then by slightly changing the objects or the constraints you're given, you can get into a situation that you will have no object of that kind. So what is our contribution? So we were able to found a simpler proof of this theorem, and actually what we were able to do is to remove the condition on the group to be abelian. So Green in his result needed the group to be abelian, and our proof also works for non-abelian groups. And we were also able, using our approach, to prove the removal lemma for systems of equations in the form that was conjectured by Green in his paper. And at this point I would like to mention that this conjecture was independently of us proved by Asaf Shapira, who actually read our paper on the other proof of a little bit more general removal lemma for group equations. He got inspired by it, and he applied, as we do, hypergraph removal lemma, but both the proofs are fundamentally different. So they reducing the problem to hypergraphs, but the way the problem gets reduced is different. So maybe I will try to sketch the differences in the last part of the talk.
So sorry, Green did his by proving a sort of regularity.
Yeah. So
you just use hypergraph.
so in the for the conjecture we use the hypergraph removal lemma, but for the group removal lemma, for the corollary he derived, we use just the graph removal lemma. So
right. Yeah, how I'm just wondering, so you guys didn't prove a regularity for non-abelian?
No. So we avoid proving any regularity statements. We just focus on proving the counting part, the counting corollaries.
Did you feel that his could be proved just using hypergraph regularity too?
You mean the regularity lemma? Yeah, well, we generalize it and we prove it. So his removal lemma can be proved, and actually I will show you the proof. And when the conjecture was proved using the hypergraph regularity lemma, and at that case the proof becomes more technical, both our proof and Shapira's proof, and I will probably just sketch a little bit what's behind the proofs, but I will not go into the details.
So how hard was the original proof?
Well, it's for combinatorists, at least it's somewhat hard because he uses Fourier analysis to derive the statement of his regularity lemma. So that might be somehow hard to digest, like for people who are not experienced with arguments of this type. Yeah, he's a Gauss student, exactly. So what I want to do, I know there should be a proof in each talk, and the proof I want to give is actually the proof of the removal lemma. So I call it sketch, but I believe I will tell you almost all the details, and what I am not, if I will just sketch something when I believe it will be easy for you to figure out the remaining details. So let me try. So we are given a group G and sets A1 to AM of the elements of this group, and we're interested in solutions of some equation of this form. So first thing that is easy to realize is that we can assume the right hand side to be 1, because if it's some element G, when you just go to new A4 var, where you put all the elements of the form, let's say A4 G inverse for A4 from the original set A4. So what you basically do is, like, if the right hand side is not the unit element, you multiply both the right hand side and the left hand side by G inverse, and you consider the products of A4 times G inverse for the elements contained in the original set as the new set A4. So that's an easy reduction. And now what I want to do, I want to reduce the group removal lemma to the graph removal lemma. So for that I will need two things. I will need a small graph that I am searching for, and a big graph in which I am searching for this small graph. So the small graph will be actually a directed cycle of length 4. So this will be this guy. And now it's important that this graph is independent of G. It only depends on M, because if it were dependent on G, then all the constants all the dependence of the constants in the statement of the removal lemma will be spoiled. So it's important this graph is independent of the group and of the sets A1 up to AM. And the big graph G0 will be constructed as follows. It will have, if M is 4, it will have 4 parts. In general, it will have M parts. And in each part, there will be as many vertices as is the order of the group, and each vertex in every part will correspond to one of the elements of the group. So these vertices will correspond to the elements of the group G. So now I have to tell you what the edges in this graph are. And if I have some element H here, when I'm going to join it by a directed edge to all the elements of the form HA1, where A1 is from A1. So the out degree of H of every vertex here is equal to the cardinality of A1. And similarly, I am going to join this guy to all the vertices such that this element is his element times some A2, where A2 is from A2. And similarly, here I will join this guy to all the vertices of the form the element corresponding to this guy times A3, where A3 is from A3. So now, if you consider a solution of the equation, so you consider this solution. So when you come back, you're actually coming back to this guy, because you're going to join this vertex to all the vertices that correspond to the element of this guy times A4 for A4 from A4. But if this is a solution, this is just a unit element, so H is equal to H. So what I see is that if I fix a solution of the equation, then whatever vertex I am going to choose in the first set, then if I follow the edges corresponding to the values of the unknown variables in this solution, I will return to the same vertex and I obtain a copy of cycle of length 4. And I obtain as many copies as I have vertices in the first part. So for every solution, I have n disjoint copies of the cycle of length 4. Because I can choose this vertex arbitrarily, and if I follow the edges, then I have these edges, and because it's a solution, when the product of the 4 elements assigned to these edges, or these edges correspond to, is the unit element, and I get back to the original vertex. On the other hand, if you give me a cycle of length 4, and I read out what are the values these edges do correspond to, I get a solution. Because if I end up here, that means that the product of this guy is unit vector, because I can cancel by H inverse from the left side. And therefore, for every cycle, I get also a solution. So I see there is a correspondence between the cycles of length 4 in this graph G0 and the solutions of the original equation with the restriction that xi is chosen from ai. But this correspondence is not 1 to 1, it's 1 to n. So for every solution, I have n cycles. So this is just a picture that I have just drawn on the blackboard, so I think I can skip it. This is just a one particular example. And let me continue. So if the equation has few solutions, because and few means n to m minus 1, so n is the order of the group, and m is the number of variables in the equation. So if there are few solutions, then, since the correspondence is 1 to n, the number of cycles of length g is of order n to m. So m in our case is 4. So meaning few solutions, and few solutions in our case would mean subcubic many. That would mean the number of cycles of length 4 is asymptotically less than n to 4. So we can apply the graph removal lemma. So here, like, you just have to realize that the number of vertices of your big graph is not n, but it's 4n. But since m is fixed, this doesn't affect the asymptotic order. It's just, in this case, it's just a multiplication of a constant by 4 to 4, in general by m to n. So we can apply the graph removal lemma, and we get a set of edges E such that GE doesn't contain a cycle of length 4, and the order of E is subquadratic. So at first sight this doesn't seem like a win, because what you would like to do, or at least I would like to do when I have seen it for the first time, I would like to remove the elements corresponding to these edges E from the set A1, A2, A3 and A4, but I can't do it because I am supposed only to remove sublinearly many elements, but this set E is subquadratic, so in theory it can be much bigger when linear in n. So what I am going to do is I am going to remove an element from a set A1 only if I get enough votes for it to get removed. So what I do mean by enough votes, so if I look to the edges corresponding to one fixed element A1 between the first and the second part, so where n edges corresponding to A1. From every vertex I have exactly one edge corresponding to this element A1. And I am going to remove this element from the set A1, capital A1, if at least n over 4 of these edges are in E. So remove AI from capital AI if at least, in our case, n over 4, in general n over m edges corresponding to it are in E. So that means there are lots of votes for it to get removed. Because of this, so if I am going to remove an element from a set, if there are at least n over 4 edges which correspond to it, so since the set is subquadratic, the number of elements I am going to remove in this way is only sublinear. Because I have something which is of subquadratic order of n, and an element gets removed only which get linearly many votes. So I am going to remove only sublinearly many elements from each of those sets. So what remains to be argued is, so I got new sets AI prime, and I have to argue that there is no solution left. So imagine there would be a solution left. So you look at the 4 cycle corresponding to it, and now what you do is you consider all the n copies, all the n cycles corresponding to this solution. There was no cycle of length 4 in the graph G0 minus E. So that means from each of these n cycles that I am looking at, so I maybe should draw them, at least one edge was removed. So I have n cycles corresponding to a solution, and from each of them at least one edge was in the set E, because there was none of them was in the final graph and were disjoint. But that means, since I have 4 parts, that there must be 2 consecutive parts, that the set E contains at least n over 4 edges between these 2 parts, and that was the element I have removed from the set AI. So no solution will be left. And that's the end of the proof. So are there any questions? Like, I realized this proof was maybe too long for a talk, but on the other hand, I think it's so simple that I'm always tempted to give it. So if there are no questions, then I switch off the light and move to the last part of my talk. And in the last part of my talk, I would like to talk about another version of the removal lemma, and this time a removal lemma for systems of equations. So Green in his paper conjectured the following. So fix a full rank matrix A whose all entries are integer, and this matrix has k rows and m columns. And think of A as a matrix which is white. So k is smaller than m. So for instance, like a particular case corresponding to one equation would be a matrix with a single row where all the entries are 1. So now we will be interested in solutions over integers, and again we will have unknown variables. The number of unknown variables will be m, the number of columns of this matrix, and for each variable we will have a set capital Xi that will restrict us the values that we can assign to one of the variables. And we will be only allowed to assign some integers between 1 and n. So the problem is we will be interested in integral solution for an integral system of linear equations. So we have a matrix A that describes us the system of equation, and for every of m variables we are given a subset of integers between 1 and n. And now the maximum number of solutions you can hope for is of order n to m minus k, because the matrix is full rank. So its kernel is of dimension k. So if you recall some basic linear algebra properties, you see that the maximum number of solutions you can hope for is of order n to m minus k. And if the number of solutions is asymptotically smaller, is less than this maximum number of solutions you can hope for, then again what happens is you can remove few elements. Few means sublinearly in the length of the intervals from which you are allowed to choose your set Xi, such that there will be no solution left. So this is the statement how Green conjectured it. So maybe before I will tell you what our results are, let me show you one corollary of this conjecture. So assume the conjecture is true. So when this will be a true statement, and let us look at the following problem. So consider two equations. x1 minus x2 is equal to x2 minus x3, and x2 minus x3 is equal to x3 minus x4. So these equations do correspond to the matrix 1, minus 2, 1, 0, and 0, 1, minus 2, 1. So this is matrix A in our problem. So what I have just done is that I moved the right hand side to the left hand side. I subtracted x2 and added x3. So I have an integer matrix which is clearly of full rank. So it satisfies the assumptions of the statement. So I can the removal lemma for this system of equation. So now I will fix a positive epsilon and consider a subset of integers between 1 and n. So there are two possibilities. So either I have many solutions to the system. But what does this system say? This system says that the difference between the first and second element is the same as the difference between the second and third, and that is the same as the difference between the third and the fourth. So in other words, x1, x2, x3, and x4 is an arithmetic progression. So if you have lots of solutions, when you have cubic, this should be 2, you have quadratically many arithmetic progressions. So this should be 2 because m is 4 and k is 2. And of course quadratically many is the best you can hope for, because when you fix the first and the second element, the third and the fourth are uniquely determined. So and the other outcome, as we will just realize, cannot happen, because if you have few solutions, then this statement would tell you that you can remove few elements from each of those sets in such a way that there would be no solutions left. So if there would be such x prime, such that x minus x prime would not allow any solution, then the size of x should be at most epsilon times n. And the reason is that if this set is non-empty, then this is always a valid solution. It's not a arithmetic progression which is particularly interested, but it's an arithmetic progression. So if the size of your set is bigger, then of course you cannot make this set empty. So this outcome can never happen, and therefore in every set of positive density you have quadratically many arithmetic progressions of length 4. So this result was of course known before, but I just wanted to illustrate the statement of the removal lemma on it. So maybe questions? Doesn't seem to. So let me move to what we proved in this framework. So we have given a proof of conjecture. Actually, we didn't prove the conjecture in the form for integers, but what we did is we proved it in the form for finite fields, and when using just some standard argument by considering the sums modulo primes which are big enough compared to n, one can easily derive the conjecture of Green. As I said, independently of us, the conjecture was proven by Asaf Shapira, who had a paper on it in Stock. He also looks like a little bit more algorithmic aspects of it. And both are proofs uses the removal lemma for hypergraphs. Shapira's hypergraphs can be of order up to m squared. So m is the number of columns, it's the bigger of the two numbers. And our removal lemma uses k plus 1 uniform hypergraphs. So the way our proof uses the removal lemma for k plus 1 uniform hypergraph. So our proof is somewhat more direct generalization of what we did, because if you plug k equal 1, which should correspond to a single equation, you get just graphs in our case. And I have to say that Shapira wrote very nice words in his paper about our proof of the group removal lemma, and he said that he was inspired by it, but his proof is not like that direct generalization as our proof. So, and as I said, both proofs were inspired by our removal lemma for group equations. So I think I have some time, so I first state a theorem, and then I will see whether I can sketch some parts of the proof. So our theorem says the following. So as I said, we're proving the version for finite fields. So what we fix is the order of the matrix. So we fix the number of rows and the number of columns, but we're not going to fix the matrix. And it doesn't really make sense to fix the matrix, because like for every finite field, we somehow need to fill in the matrix with the elements of that finite field. And then for every q element finite field, if we consider a full rank matrix with k rows and m columns, we consider arbitrary right hand side. So the right hand side, the system of equation doesn't need to be homogeneous. And we consider sets x1 to xm that restrict individual variables, when if the number of solutions is asymptotically smaller than the maximum number of solutions you can expect. So if these sets x1 to xm were all the elements of the field, then the number of solutions you would get would be q to m minus k, because they would, the solutions, the kernel of the matrix would have dimension m minus k, and therefore the number of solutions would be exactly q to m minus k. So what we're saying is if the number of solutions with respect to the sets x1 to xm is asymptotically smaller, then again you get the same conclusion. You can remove few elements, and few means sublinear in the order of the field in such a way that there would be no solution left, and no solution of the equation ax equal to b, where the ith coordinate of the vector x should be from the set xi. And as I said, the version we're proving is non-homogeneous. The right hand side doesn't need to be equal to the 0 vector, and the constants we have, they do not depend on the matrix A, they just depend on the number of rows and the number of columns of this matrix. Yeah?
Is it obvious that this implies Green's theorem?
It's almost obvious, because what you're going to do is, like, you have lots of primes which lies between, like, exactly, so you just consider the original equation modulo these primes, and then you get the result. Or maybe not between n and 2n, but between n times m and 2n times m, or something like that.
But, I was worried about full rank, so
A matrix which is full rank over the real.
It's an integer matrix, and again this can be fixed by, like, so not always you will take n, but you will take n from some n0 on. So if you have an integer full rank matrix, it stays full rank if you're choosing suitable primes big enough. So this is not,
I almost believe.
yeah, like it's not an issue. It's really simple. So maybe, since I have 10 minutes left and I want to leave some time for questions, I will skip the sketch of the proof, and I show you the pictures, which maybe tell you a little bit more about the proof. So this is the graph we're searching for in the proof for group equations. It was just a cycle, and for every element contained in the set A1, there was an edge. So the edges were just pairs of vertices. So there is one particular case in which the lemma can be easily proven for the system of equations, and it was done even before us and before Shapira by Candela, who is a student of Gowers, and it was the case where if you have this matrix A, when every k consecutive columns they form a full rank. So you have this matrix A that determines you this system, and the special case that is easy to do is that if you take, so k is the number of rows, m is the number of columns, and the special case that's easy to prove is that if you take any k consecutive columns, then you get a regular matrix. And in this special case, the graph, the hypergraph you're searching for is just a hypercycle. So you have just vertices on a cycle, and if you have two equations, then every 3 consecutive of them form an edge. In our proof, you have to do, so this proof is a generalization of our proof for groups, but if you want to get a proof in the general case, sometimes you will not be searching for a hypercycle, but sometimes you have to jump. So this is depicted here. So this is type of a hypergraph we're searching in our proof. And in Shapira's proof, I think you're searching for the nicest of the hypergraphs. It's like a flower. And what basically is happening is that the vertices that are in the center of the flower, they kind of determine which of the solutions you will be interested in. So they kind of choose the coefficient of the appropriate linear combination of some base vectors that would give you the solution. It's not completely true what I said, but let's think it's like that. And when the vertices in the petals, they will tell you something about the actual values of the unknown variables. So maybe I have still time, I would say, to viewers about future research that I have been working on for the last few months, with David Ferguson, who is a student of Josef Skokanen, who was visiting our department in Prague for half a year. So we were looking whether we can generalize the group removal lemma, which is a statement about a linear equation. It's easy to generalize to arbitrary linear equation over finite fields, but we were interested whether you can say something about polynomials. So the statement is that if you have the sum of 4 unknown variables equal, let's say, to 0 or to something, when it's known. So the group removal lemma says that if this function is linear, then you have the removal lemma. So the question we were looking is whether you can say something about polynomials, like for instance this one or this one, and the answer is that we can state the lemma, we can prove the lemma for this polynomial, but we can't prove it yet for this one. So this is just a work in progress. That for some polynomials we sure the lemma holds, and for some we still don't have the argument, but we strongly believe the lemma holds. And since I want to leave some time for questions, I think it's time to thank you for your attention.